Hey guys, welcome to the channel. My name is Mehran. I'm a final year PhD student in applied math, and today we're going to be talking about selfish behavior, why it is ineffective, and how we can avoid this using incentives. Let's see how selfish behavior can be inefficient by an example. Assume there are 10 cars that want to travel from a starting point A to a point B. There are two roads between these points. The first road is short but narrow. So the time it takes to go from A to B depends on how many cars take this road. If only one car takes it, then it only takes 1 minute to get to B. For two cars, it'll be 2 minutes for each car to arrive to point B. So in total, 4 minutes for both. If all 10 cars choose road 1, then there will be traffic and each car has to wait 10 minutes. So for each car, the travel time of the first road is equal to the number of the cars that are on the road. The second road is a highway, but it is longer than road 1. If a car takes road 2, then it takes 10 minutes to get to point B, no matter how many other cars are on the road. Now the question is, what happens if the cars are selfish? Let's look at just one car. If it takes road 1, in the worst case scenario, everyone else has also taken road 1 and he has to travel 10 minutes to get to B. But if he takes road 2, he will for sure has to travel 10 minutes. So he takes his chances and chooses road 1. But he sees that every other car is also there. This is because every other car is also selfish and thinks the same way. So they all end up in the first road. So for all the cars, it takes 100 minutes to get to B. Not a great scenario, especially since this 100 minutes is the worst travel time that can happen. To see this better, let's look at another scenario. This time, the cars split between the roads. So 5 cars take road 1 and the rest choose the second road. 5 cars in the first road means it takes 5 minutes to get to B. So the total travel time is 75 minutes. This is less than 100 minutes that happens when every car only thinks about themselves. We see that selfish behavior is not efficient. To avoid this, we can use some interventions and motivate people to work together. But the question is how? Game theory and network games could give us the answer. A common way to look at the relationship between people is network game, and it models the interaction by a graph. Every circle models a person, and the arrows show who is affecting whom. To model how much a player J is influencing a player I, there is a weight for every link. If there is no relation between some players, then their weights are 0. So the influence of all the neighbors of player I is the weighted sum of their decisions. To be a bit more formal, let's call xj as the action of player J, and x, that is the collection of all the actions, as the action profile. For the intervention, a system regulator chooses incentive signal UIs. The players want to do what is the best for them. To model this, we think of a payoff function that they want to maximize. There are a lot of papers that suggest different payoff functions. A standard one has this form. The scalar A models the impact of the neighbors, and BI is known in the literature as the standalone marginal return. In case you are interested, I put the link to a paper that justifies this function in the description. Because the players are selfish, they want to do what is the best for them. So each player wants to take an action that maximizes his payoff function. The regulator's goal is different. He wants to find incentives that motivate the players to work together. So his goal is to find UIs that maximize this summation of WIs. Now the question is how the players and the regulator try to achieve their goals. Let's look at the problem that players want to solve. Each player I wants to maximize his payoff function UI. So he wants to solve this maximization problem. clearly the solution of this problem depends on XJs, but also the other players want to solve a similar maximization problem. So all the players together want to solve n-coupled maximization problems. One way to find the solutions of these problems is to use pseudo-gradient dynamics. It is called pseudo-gradient since we only take the partial derivative of ui with respect to some of its variables, which is actually xi. Doing a bit of calculation, we see the explicit form of the dynamics is the following. Also, the action profile of all the players is the solution of the dynamics. Here In is the n by n identity matrix, and the matrix P has this form. Now that we know how the players make their decisions, let's look at the regulator. The regulator wants to motivate the players to cooperate, so he wants to maximize the summation of WIs. More formally, the regulator wants the action profile of the players to go to xopt, that is the solution of what is known as the social welfare problem. Using the expression of WIs, then the optimization problem has this form. Before moving ahead to see how the regulator can find the intervention signal U, we have to see when xopt exists. Here is the answer. There is a unique xopt when the parameter A multiplied by all eigenvalues of P plus P transpose are less than 1. Also, the explicit form of xopt is given here. To sum up, we have a connection between selfish players and the regulator. The players use a pseudo-gradient dynamics to choose their actions, and the regulator wants to find incentives that take the action profile X to the social optimum xopt. Now, if the regulator knows everything about the players, he can easily find the incentive. In fact, the incentive that works has this form. But of course, in practice, there is no way that the regulator fully knows all the players. So his job is much harder. Let's look at a scenario that the regulator only knows xopt. As you saw before, the players interact with the regulator. Since the regulator knows xopt, he first finds out how much x is different than xopt, then takes the integral of the difference to find u. This way, if the actions are different than the social optimum, then the signal u keeps track of the error and updates itself to make the error 0. In the end, the actions will go to the social optimum. If you are interested, there is this paper that has all the analysis, and its link is in the description. By the way, the incentive u will converge to this value. This is exactly the one that the regulator can use if he knows everything. I find it quite interesting, don't you think? So I guess the takeaway is that when people act selfish and only for their own benefits, what they get in the end is actually worse. We see this everywhere, like electricity consumption and in traffic. The effect gets even worse when the resources are limited. So that's why incentives can help to motivate people to work together and do what in the end is the best for all. Thanks for watching and hope to see you in the next video.